So that was where we ended last time. Okay. So this one. Okay. Okay, we have started on metal complexation reaction. So we will need to deal with ligand, right? So the ligand comes from a chemical that itself is a weak acid. Okay, now if you mix the two chemicals, you will be curious how they react to form the product, right? Without adjustments to the pH. Okay, so now you have the two chemicals mixed simply. Then you will see that if we use the symbol KPD, is proton displacement constant, but just call it equilibrium K, just another K, okay, equilibrium. So looking at the first reaction, that K, let's call KPD1, is going to be equal to KF1 multiplied Ka. Now what's the point here? Well, the point here is you have a Ka magnitude multiply the Kf magnitude. You look up the table, okay, both of them are available. Ka will be typically 10 to the minus something, so it appears to be small. But then Kf usually is large, so you must simply multiply the two, then you can predict how much product going to generate, whether the reaction will drive to the right. So as you can see, the reaction is still going to drive to the right, but a relative magnitude. To prove this formula to be true, okay, so here is a proof, okay. Now you look at the reaction. So Kf1 is equal to product over reactant like that, okay. So this is the definition. Now you multiply the definition for Ka. While the two definitions multiply each other, cancellation for the L minus, then indeed it indicates reaction number one, right? So this is just to prove the formula to be true. Then similarly, continue, the first product going to react with more of the ligand, which is the Ka, to give the ligand, then it's going to be Kf2 multiplied Ka. So the proof is similar to that, okay? So at home, you can write out the definition for Kf2, okay? Plug in the Ka right here, multiply the two to see whether you end up with this, okay? And this corresponds to the second reaction. So that in the future, you will feel confident the application of simply multiply the two Ks, okay, for the situation like this, okay? So any question with that? So the key point here, again, is just the application of Kf and Ka. And here, the Kf and Ka. Okay? So keep that in mind at this point. Okay, we need to understand more on the Ka, particularly polyprotic acid. Like Jeremy last time asked about, what about the two Ka values are near each other? Okay, so here is an example. So Ka1 approximately equal to Ka2. Then how do we calculate based on our assumption? So analytical concentration, let's say is 0.02. Then the two Ka values, the first one is always larger than the second one, but in this case, it's not by much, okay? 10 minus 3, 10 minus 4. So the point here, now we want to look at whether Ka2 will contribute to the total proton, okay? Because pH is based on the total proton concentration. So if we assume Ka1 only, remember previously we assumed polyprotic acid SF monoprotic and use Ka1 only to calculate for the pH. So let's do this assumption again. Use Ka1 only, then it's going to be x squared C minus x, the usual, right here, right? The usual. Any question with this usual? Okay, so the x represents the total proton. Okay, solve the x. So the usual assumption here, now this is the Ka magnitude. Take the square root of this, estimate for this x. So with that, then this x is not going to be negligible, right, relative to this number. So you will need to use quadratic equation. So you do the labor work at home, verify this. Okay, quadratic equation. Then you end up with a total proton to be 5.4 times 10 to the minus 3 molar. So this represents the total under this assumption. So keep this in mind. Okay, so look at the whole picture. You start with this guy, okay, then this concentration is going to ionize, generate the X here, and generate the X also. So this X is equal to that X, right? So at equilibrium, then it's minus X. So this is Ka1 situation. Okay, so you have no problem with that. So now we're going to include Ka2 into the picture. So this guy now is going to ionize into this guy as well as this guy. So this is going to generate the X for A2 minus specific for this acid. Now this is called acid. So this quantity is specific for that, and it generates the X. So this X is not that X. So this is a crooked italic X, and this is capital letter X. Okay? So we generate this X simultaneously, right? Equal X, so the capital X. So let's call that the second proton, capital X. Okay, then this one here, the X. Now notice the X, we just calculated the X, right? So this X is 5.4, so now minus the capital letter X, so this total is going to subtract the X to generate this second proton. Okay, so we will proceed with this point on. Any question with this picture? Yes?
So the X from the first part becomes the HA concentration for the second, is that?
Okay, this X now referring to HA, but HA minus this X is calculated to be this magnitude.
Right.
But this total amount, a portion of it is going to ionize. Okay, so a portion of it is going to ionize into that. Okay, so what this picture continues,